Hello everyone, my name is Fernando Castillo Vicencio. In this video, I will present the parametric development of the OpenFOAM cavity case by using Salome and Python to make geometry and mesh, and Shellscript to make an automation of the process. This type of development, this type of solution can be used to run multiple and automatic flow simulations without opening any interface. With just one command, we can perform the entire CFD process, saving time in drawing geometry, making the mesh, or running the OpenFOAM case. For example, we can see here the cavity1.sh command. Cavity1.sh command. Here we have the Salome processing to make geometry mesh. The next step is the OpenFOAM calculations. And finally, we can see here the simulation results in ParaView. Okay, we have the mesh and results. Okay, velocity, and this is the cavity case. Well, I divided this video into 4 steps. The first step is the problem and specifications. The next steps are geometry and meshing using Salome and Python. The final step is the coding automation by using Shellscript. Now we will start with the problem and specifications. The problem is the well-known cavity case found in OpenFOAM tutorials with a moving wall of 1 meter per second, with 3 fixed walls and 2 face front and back. Okay, the dimensions of this domain, the cavity domain, are 8b and t. A is the height, b is the length, and t is the thickness. These dimensions and this free stream flow velocity are variable and can be changed at any time. Well, my hardware is a 2013 hardware. I have an Intel Core i5-4690K quad-core processor. I have a 32 GB of RAM and a Sapphire Radeon R9 290 graphics card. Currently, I'm using Arch Linux operational system with E3 Windows Manager using kernel 5.4. The main software used in this video is OpenFOAM 1906 from openfoam.com, Salome 9.3, and Python 3.7. There are other optional software as Visual Studio Code, LX Terminal, and Perl for text replacement. The second stage of this video is the geometry. The geometry can be divided into 4 steps. The first step is to set the geometrical parameters. The second step is to draw the geometry, drawing in this order the base sketch, the base face, and the extruded cavity domain. The third step is to set edges for meshing, like side edges and base edges. The final step is to set the boundary conditions, like moving wall, fixed walls, and front and back. Well, at this point, how the geometry is made? Well, to begin, it should be pointed that these 2 files will be used. The cavitymesh.py to generate geometry mesh, and the cavity1.sh to make the automation of the process. This other file is the cavitymesh.umv. This file is the mesh generated with Salome. Now, you can delete it now. Well, now we will analyze the cavitymesh.py file. As you can see here, this code begins by importing the necessary libraries for Python and Salome. Okay? To know which libraries to import, we can open the Salome interface and the geometry module. By saving this file, I will save this file as test.py and opening this created file, you can see here the appropriate libraries to import. It is precisely this script that I used to make this video. The first step to open the geometry module is to import the libraries. Okay? Let's import the libraries. The next step is to set the origin and the axis of the rectangular coordinates. Now we can create the geometry. The first step is to assign the geometrical parameters as A, B, and T, height, length, and thickness. Well, to draw the geometry, we have 4 steps. The first step is to create 4 vertices, the 4 vertices of the rectangle, by using the command make vertex. The rectangle has an area of A times B. The second step is to create the 4 lines of the rectangle by using the command make line to point. The third step is to create the base face by using the command make face wires by joining the 4 lines created before. The last step is to create the cavity domain by using the command make prism two ways, which means the extrusion of the base area, the base face, in the OZ axis with thickness of T over 2. The next command is to add to study the cavity domain to the Salome interface. Now this script can also be executed from Salome interface. Okay, as you can see here. Okay, load script and cavity mesh.py. You can open the geometry, and this is the cavity domain. Okay, this is the cavity domain created with the script. Okay. Now the next step is to create the edges formation. The first group of edges is the called side edges for meshing along the thickness of the domain. Okay, along the thickness of the domain. These 4 edges. Okay, by using the command create group and choosing the edge shape type. The IDs of side edges can be obtained from the geometry. From geometry. Okay, as you can see here, we can obtain this ID by using the command create group. Okay, main shape, cavity domain, and we select the edges. Okay, edge. And here can we see the edges selected in this code 5, 8, 15, 22. Okay. Similarly, we can create the base edges by using the command create group and selecting the edges with ID 11, 12, 18, 19, 25, 26, 29, and 30. Well, the next step is to create the boundary conditions. Well, in this problem we have 3 boundary conditions: the moving wall with a velocity of 1 meters per second, the fixed walls, the 3 fixed walls, and the front and back faces. These boundary conditions can be created by using the command create group and choosing the face shape type. The moving wall has the face number 3. The fixed wall have the faces 13, 20, and 27. Similarly, the front and back faces are the faces 31 and 33. Now we can see these boundary conditions and mesh edges in Salome interface. Okay, we can see the side edges, the base edges, and the boundary conditions, moving wall, fixed walls, and front and back faces. Okay, front and back faces, the fixed walls, and finally the moving wall. Now the next step, the third step, is the mesh. Okay, meshing. The mesh can be divided into some sub-steps. The first step is the mesh parameters. Set global mesh method in 1, 2, and 3 dimensions. The sub-mesh of selected edges. Compute mesh, set boundary conditions, and export mesh to a UNV file. Okay. Well, the first step for meshing is to import the necessary libraries to open this module in Salome. Okay, this module is here. Okay. The next step is to set the meshing parameters. In this case, we can define two parameters: the number of segments in the base edges and the number of segments of the side edges. Okay, these parameters may be changed at any time. Now we can create the mesh by using the command smesh.mesh. Okay, the next step is to create the mesh method, the mesh algorithm, for 1, 2, and 3 dimensions. Well, for 3D, we select the hexa method for hexahedrical elements. For 2D, we select the quadrangle method for quadrangular elements in the faces. Okay. For 1D, we select the segment method, which means that the edges will be divided into a determined number of segments. Note that by choosing some methods, as for example mghexa, we may have errors when converting the mesh to OpenFOAM. Well, at this point we can create the one-dimensional meshes, sub-meshes. For example, we can select the edges pointed out, base edges and side edges. Okay, by using the segment method, in this case for base edges, and in this case for the side edges. Okay, in this case we can use these variables to make the divisions. These variables to make the divisions of these edges. Okay. Well, the next step is to compute the mesh by using the command compute. Now we can associate the boundary conditions created in the geometry module into the mesh by using the command group on geometry. Okay, in this case we made this procedure in the moving wall, fixed wall, and front and back faces. Okay. The next step is to export the mesh to a UNV file by using the command export UNV file name. The last command in this code is to update the Salome object, the Salome geometry and Salome mesh for using in the Salome interface. Okay. Well, here can we see the mesh and the boundary condition of this mesh. Okay, here can we see the mesh. These edges are divided into 20 segments. Okay, this is the moving wall. There are the fixed walls, and there are the back and front faces. Okay. Okay, now we have the cavity1.sh, and this is a Shellscript code. Okay, the first step of this code is to assign the parametric variables for this problem. Okay, we can see here the free stream velocity, the dimensions of the domain A, B, and T, height, length, and thickness, and the mesh variables. Okay, described before. It should be noted that these variables can be changed at any time. The next step is to replace these parameters into the Python script by using Perl. Okay, the syntax of Perl is Perl -i-0pe as hash text1 hash text2 hash for replace text2 over text1. Well, in this case, we have the replacement into the geometrical parameters and the mesh parameters. Okay, in the cavitymesh.py file. Okay, those are these lines, geometrical parameters and the mesh parameters. Okay, the next step is to run the Python script in Salome. Okay, we have some previous steps. Okay, such as determine the current directory as workdir variable, the case name as the cavity. Okay, and to replace the case name into the Python script for exporting the UMV mesh, and by using Perl. Okay, the next step is to remove all UMV meshes, and finally we can run this script, okay, by using the command salome-t cavitymesh.py. The next step is to copy the cavity tutorial from the tutorials to the cavity run case. Okay, we have the cavity run case here. OpenFOAM, Fernando, run exercises, incompressible cavity, and this is the cavity case. Okay, this is the case there, the case directory. Well, the next step is to copy the UMV mesh from the cavity directory, from the work directory to the case directory. Okay, to the case directory. Okay, the case directory is in the OpenFOAM run folder. Exercises, incompressible, for me, incompressible, cavity, and cavity case. Okay, this is the folder. Okay, the next step is to import the mesh by using the command ideas UMV to foam, okay, space cavitymesh.umv. Okay, this is the mesh. And finally, we can check the mesh by using the OpenFOAM command check mesh. It should be noted that this command, this OpenFOAM command, only can be used if the terminal used has the OpenFOAM activated. Okay, in this case, we can activate OpenFOAM by using the command OFOAM. Okay. The next step is so important because the importation of the UMV mesh has an important disclaimer. Okay, when importing the mesh, we generate the polymesh folder with some files. Okay, but in the boundary files, the boundary conditions are all imported as patch. Okay, so we need to change this type of boundary. Okay, but how do you know this? Well, we can see the appropriate boundary conditions in the file 0p. Okay, as you can see here, the moving wall is 0 gradient, the fixed walls are 0 gradient, and the front and back is empty. Now we can make the replacement. in the cavity1.sh file by using the per command. Okay, as you can see here, we have the replacement in the moving wall, fixed walls, and front and back. Okay, all in the same file, the constant polymesh boundary. Now the next step is to replacement of the flow velocity in the 0u file. Okay, by using the per command. Okay, we can use the variable u infinity defined before. Okay, and finally we can run the icofoam and the parafoam commands. Okay, at this point it should be noted that this file cavity1.sh must be executable. Okay, we can do it by using the command chmod. For example, we have the cavity1.sh file. Okay, and we use the command sudo for admin chmod /cheese cavity1.sh. Okay, and then we can run this case cavity1.sh. This is the Salome module, the Salome processing for mesh and geometry. This is the OpenFOAM calculations, and finally we have the cavity results in ParaView. Okay, this is the mesh, this is the case. Okay, now we can change the parameters of this case. Okay, for example, we can change this parameter to 1.5, this parameter to 40, this parameter to 3, and the dimensions to 2.0. Okay, we need to save this file, and now we can run the case. Okay, this is Salome processing. Now we have the OpenFOAM calculations, and finally we have the simulation results in ParaFOAM. Okay, this is the case, this is the mesh. Okay, this is the velocity, and this is done. Okay, thank you very much.